All right, guys. So one of the things that we want to do now is introduce a new mathematical tool, a very powerful one called Laplace transform. Now, to kind of put everything into context, when it comes to the IV characteristics for the resistor, the capacitor, and the inductor, one of the things that we saw is that the IV characteristics are no longer algebraic in form. They are indeed differential equations. And through the use of KVL and KCL, as well as different techniques of circuit analysis, things like the node voltage method, the mesh current method, one of the things that we can do in order to analyze any sort of circuit is we can use those in order to set up systems of ordinary differential equations, which hopefully, when solved, will give us the parameters of interest. Now, when it comes to the solution of differential equations, there are multiple techniques depending on the type of differential equation that you have. Some equations are first order, some are second, some are third, some are fourth, so on and so forth. Some are linear equations, some are not so linear equations or nonlinear ones. And mathematicians have come up with this complete slew of different techniques that can be used in order to solve different types of differential equations depending on their mathematical form. One thing that the Laplace transform has the advantage of over all of these other different types of techniques of solution is by appropriately using the Laplace transform, one of the things that we can do is we can replace systems of ordinary differential equations with systems of algebraic equations, which I'm sure everyone will agree are much easier to solve. And then what we do is we take what we call an inverse Laplace transform to get our solution in the time domain, right, where we wanted the solution. So one of the things that I want to do very briefly is give you kind of an overall breakdown of why it is that the Laplace transform is defined and where it's going to end up being useful. So this is the Laplace transform. This is an introduction to it, and this is kind of an overview. Now, the basic idea is the following. Suppose that we start with a problem in the time domain, and there's some sort of parameter of interest that we're actually looking for. Maybe we're looking for some sort of function f of t. So here we're looking for f of t, right? Um, Now, in the time domain, what we do is we have, for f of t, we have a linear differential equation that will, when solved, give us that, right? So here, this is where we start with our idea. And the idea is we actually want a solution for f of t in the time domain. Now, the problem is that to get to the solution inside of the time domain, and I'm going to put this in red, in general, this tends to be relatively difficult, especially if your sources themselves are not perfectly DC sources and if they're not even sinusoidal sources. So if you had some sort of generalized input that is driving your voltages and your currents, in general, this is very complicated. So one of the things that we can end up doing is we can perform on the linear differential equation, we can perform what we call a Laplace transform. So over here, what we do is we move from the time domain into a different domain. called the Laplace domain. So let's separate this. At the top here, let me also say that this right here, this solution in the time domain, this is our goal, to find this. Up here, we are in the time domain, while down here, we take the linear differential equation, we perform a Laplace transform on the differential equation, and we end up with a Laplace transform equation. So down here, we are actually in the Laplace domain. And this step here is relatively simple. The reason it happens to be relatively simple is because when it comes to various common functions, the actual Laplace transform of that common function, you can use various tricks and tables in order to actually get the Laplace domain or Laplace transformed equation. Now, the beauty of this is that once you actually have the Laplace transform equation, one of the things that you can do is you can then find the Laplace domain solution here. And the step in going from the equation that we want to solve to getting to the solution in the Laplace domain, this is also relatively easy. Why? Because all we require is algebra, right? And everybody here knows how to solve equations that are algebraic in nature. Now, again, the goal is to get the time domain solution. So the last step in getting to our goal is once we have our Laplace domain solution, we can perform what we call an inverse Laplace transform, which is relatively simple. It's, again, the type of thing that you can look up in a table, and we end up with our full-time domain solution. So one of the things that we're doing is we are skip going and solving the linear differential equation using all of these different techniques. We turn our linear differential equation by using a Laplace transform into an algebraic system of equations. We then solve that system of equations. We perform an inverse Laplace transform, and then we end up with our time domain solution. So this is kind of the overarching picture as to what it is that we're actually doing for this next full chapter. And stay tuned to see how we can actually do this.